I'm not going to do that. Ionic charges, that was a part we skipped. Okay, your textbook has a nice little image, a nice little slide that shows the elements that you need to know charges for. Right? So these would be ones that at least as the textbook is presenting it, you'd have to memorize. I will make a couple minor adjustments. And that would be it. Okay, that is the adjustment I'm going to make. Tin and lead, do not memorize the charge on. Okay? What's shown up here, you need to have the charge memorized. And unfortunately, I forgot I have to add a couple in just a second.
Okay, never mind. You just said it.
I just said it? Okay, good.
Zinc,
Yep.
cadmium, and silver.
Cadmium and silver, you do need to memorize, +2, +2. Okay? So that slide now has everything that you need to memorize as far as the charges. Okay? Yes?
Would mercury have a +2 charge then?
We don't even want to worry about it.
What I'm saying, okay. It would make it easier to memorize though, that whole entire, is there a trend?
There is a trend. The reason we don't have you memorize it is that it does change. Okay? So the ones you're being asked to memorize are the ones that whenever they are an ion, this is going back to ionic charges, okay? That is the charge associated with them. They must be an ion. Okay? Is there another way that we could look at this? Okay, well, a term that gets floated out there, isoelectronic. Iso is a root, means same. Electronic means electrons. So when we're looking at our charges, we're really just saying the atom has the same electrons. Well, the same electrons as what? Okay? Our charge is really all established based off of the noble gases. Okay? How many of you in here, if fairy godmother or father came down and said, I will make you part of the nobility? You'd be like, no, I don't want to do that. You're going to be like, nobility? Really? Like the billions of dollars, the castles, the servants? You're going to give me all that? Just by doing like magic? You're going to be like, yep, give me that?
Yeah, what are you waiting for?
Yeah, what are you waiting for? Let's go ahead and do it. Okay? We don't have fairy godmothers or anything like that, or fathers. So what do we do to make everybody think we're at that level? What's that? Okay, we could lie. How do we lie? What do the nobility look like?
There's usually documentation, actually.
They have some documentation, true. Let's keep going. A crown. Where do you get a crown? Jewels. Requires money. Anybody wear jewelry? Why do we all start wearing jewelry? Okay. You're like, guys are like, I don't wear any jewelry. How about that watch? How about your cell phone? How expensive was that cell phone? Okay. We aren't nobility, and yet we are dropping money right and left on very expensive things so that we can stand out and look wealthy. Okay? Because if we don't do that, everybody looks at, oh, you're poor, man. You suck. Like, what? That's not even fair. Okay? I'm probably a better person than the nobility, but I'm not going to spend my money on something that's like that. I don't see the reason to do that. Okay? The nobility have all those tools. We try to look like them, even though we can't. Okay? We can't change who we are. We can't change our lineage. But what can we do? We could change our appearance. We could put on makeup. Okay? We could get a crown. Put on a nice plush robe. Okay? We could pay people to make us look healthier. Right? To make us look like the nobility. So we change our outward appearance. Guess what atoms are doing? The exact same thing. Atoms are made up of what three particles? Neutrons, protons, electrons. What happens if I change the neutrons?
Change the mass.
Changes the mass. When we think about the nobility, do we see big, fat people?
Yes.
Yeah. That actually
Depends on the time frame. Right? But typically, think about nobility now. No. Okay? So we aren't going to change the mass of the particle. That doesn't really do much to make our atoms noble. What about the number of protons? What if I change the number of protons? Wouldn't that make them noble? Yeah, it would. But am I not atom anymore?
No.
I will make you the nobility, but you will be dead. What? Okay. You can have billions of dollars to spend however you want, but you're dead. Not sure I accept that offer. Okay? So changing the protons changes the identity of the element. We can't change that. So what's left? Okay? Go for it.
We're in the middle where it's like AG and then it just says plus. Is it plus 2 or
Plus 1. So I can't change the neutrons, I can't change the protons. The only thing left is to change the electrons, also known as same electrons, isoelectronic. We're concerned about changing the electrons. Okay, so let's pick an element. What element do you want to look at? Oxygen, I think, was the first one I heard. Okay. I will look at fluorine too, but I'm going to also identify magnesium. I needed 2 of these. We started with oxygen. How many electrons does oxygen have?
How many electrons?
Electrons. Okay. We can get 2 answers, 6 and 8. Okay. What is the 6 in reference to? The valence electrons. I just asked for the electrons. This argument works both directions, either using the valence or the total. I, for whatever reason, prefer to look at the total. So I'm just going to write 8 there for 8 electrons for the oxygen. Okay. Oxygen now wants to look like the noble gases. There are 2 noble gases that are closest to it. What are those 2 noble gases? Neon and helium. Okay. How many electrons does helium have?
2.
How many electrons does neon have? 10. So for oxygen to look like the nobility, it has 2 pathways. Okay? It can look like helium by doing what? I don't accept losing a lot of electrons.
Losing like 6 electrons.
6 electrons. Or, which is easier? Gaining 2. So if oxygen gains 2 electrons, what happens to its charge? It becomes negatively charged. It becomes negative what? Negative 2. It only gains 2 electrons. So when we look at the charge on oxygen, it went to a minus 2. 8 plus 2 more electrons to be 10 gets me a negative 2. Okay. The charge there is what we're trying to determine. So I think that's what you were saying you were doing. Okay. What we're trying to say is, where did that charge come from? Okay. It is easiest for oxygen to gain 2 electrons, so its charge will become negative 2. Okay. Well, maybe that only works for the negatively charged species. It doesn't. Works for everything. But let's prove that. Okay. We had magnesium on the other end. How many electrons does magnesium have? 12. What are the 2 noble gases closest to magnesium? Okay. And it's a good one to pick because we're now offset, right? We're not looking at helium again. We're looking at neon versus argon. Okay. For magnesium to look like neon, what has to happen? Okay. Why does it lose 2? How many electrons does neon have? 10. Argon? Argon? 18. So for magnesium to look like neon, what does it need to do? Lose 2 electrons. Or gain, what are we? 6 electrons. Everybody see that? Which is easier? Lose 2. Less stuff to have to worry about. Okay? If it loses, wouldn't it become negatively charged though? Why not? We have to remember that our charge on an electron was negative, and that if I lose 2 negatives, I become 2 positive. There's the charge for the magnesium. I don't have to memorize it. I just have to realize they're trying to look like the noble gases. Oh man, that's really hard to do because I never want to be a billionaire. Oh wait, I do. Okay? All I have to remember is my own natural tendencies. Okay? I want to become a billionaire. I want to look like the nobility. Okay? What happens, whoops, sorry, as we offset around? Okay, let's erase everything. Someone said fluoride or fluorine. Fluorine has how many electrons? 9. What's the closest noble gas for fluorine? Neon. How many electrons does neon have? 10. What does fluorine want to do? Gain 1 electron. It could also look like helium. It could also look like argon. To look like helium, what has to happen? It has to lose 7 electrons. To look like argon, it would have to gain 9. Okay? Look like krypton. It could do that too. It's gaining even more. We're looking for the smallest number to transition. Make sense? Okay? Yeah. Let's pick another one. Let's pick carbon. Are you told to memorize the charge on carbon? No. I wonder why. What are the noble gases closest to carbon? Helium and neon. To look like helium, what does carbon have to do? Have to lose 4 electrons. To look like, what's the other one? Neon. Gain 4. Which is easier? They're the same. Which means which charge is correct? It could be. And as soon as we make that statement, it could be, we stop memorizing it because it can be different. Right? That's why we stop memorizing charges, is because a lot of those elements have multiple pathways to look like noble gases. Okay? We could go through and do similar analyses for zinc, cadmium, and silver. However, and this is the big however, it involves looking at the d orbitals, which makes that vastly more complicated to evaluate. Okay? So here's where I will step in and say, for the sake of the course and time, let's memorize 3 ionic charges: zinc, cadmium, and silver. The rest of them I can derive off the periodic table. Okay? Non-metals, unless it's questionable, or group 1 and group 2. Make sense? Okay? This generates our ionic charges. That's all ionic charges are. Okay? A good question might be, where did oxygen get the electrons from? Okay? Because we don't have just electrons chilling, floating around. How did oxygen get those electrons? Magnesium didn't want electrons. Where did it get rid of those electrons to? Okay? They're giving them or taking them from atoms around them in an ionic compound. Okay? So when I bring an element of magnesium and oxygen near each other, they will trade electrons according to these charges. Okay? That gets us to our ionic compounds, okay? Which, I'll come back to this. Nope, I won't. What the? Okay, I forgot to copy some slides over. So we'll come back and look at those slides later. Okay? When we were looking at our Lewis structures, we had 2 different types of bonds, ionic and covalent. Okay? Those classifications on knowing what is ionic and what is covalent are really important classifications, because that allows us, come on, to deal with our ionic charges. If I have a covalent compound, do I care about the ionic charges? So another way, if I have an ionic compound, do I care about the ionic charges? Yes, because both of those involve the word ionic. If I have a covalent compound, do I care about the ionic charges? No, because it doesn't say ionic. Right? So you need to be able to look at a compound and say that is ionic, that is covalent. How would we differentiate between our ionic and our covalent? We could look for a charge. Just because Greg almost died doesn't mean you have to keep laughing at it. We have 2 compounds. Only to the 2 people in the back who can't breathe. Two compounds. Which of those is ionic? First definition I heard for ionic was I see ions. Do we see any positive or negatives? No. So the positive and negative may not be specified. Which of those is ionic? Sodium chloride. Yeah, that's an L. Everybody gives me crap for that. I don't understand.
I thought it was an E maybe.
That's in cursive L.
People can't read cursive anymore.
Is that better?
That's the only thing cursive could That's why
Oh, that's fine. That's fine. Try and fix it. I keep getting people telling me, what is the compound sodium with uranium? No, it's chlorine. Okay, back to the point. Why is sodium chloride ionic? Goes back to the definition of our bonds. An ionic bond is one between a metal and a nonmetal. What is sodium? A metal. How do you know it's a metal? It's on the left-hand side of the periodic table. This is why we use the periodic table and classify our metals and nonmetals. What kind of compound is water? Or bond does water have in it? Why is it covalent?
Because it's a non-metal and
Non-metal
non-metal.
and nonmetal gets classified as a covalent bond. How do we know they're nonmetals? They're to the right of that staircase on our periodic table. So those simple pattern recognitions can set us up to classify the compounds. Okay? Which means when I look at sodium chloride, I know that sodium is a +1 charge, and I know that that chloride will be a -1 because kind of that's how it is. Sodium as a metal, I know it's an ionic compound. Sodium to carry a charge wants to look like a noble gas. What noble gas is closest to sodium?
Helium.
Helium. Right? To look like helium, what does... Wait, where did I went? Where's sodium? Sorry.
Yeah.
Did I point at lithium?
No, you pointed at
Okay. So we were both completely on the wrong wavelength. Okay? So neon is the closest one. How many electrons does sodium have? 11 electrons is neon. 10. What's the easiest way to transition? Lose 1. Sodium becomes a +1. There's the charge. Chloride. Closest noble gas? Argon. What does chloride have to do to look like argon? Gain 1 electron. It's a -1. So I can specify those charges and attach them to them. Notice that I'm writing those charges in a particular place. I am not writing them in the upper right-hand corner. And that's because the upper right-hand corner is reserved for that compound. I'm specifying the charges well underneath because I'm just saying as a separate line entirely, this is the charge. I'm trying to not confuse it within the formula. That's it. When I move to water, what is the charge on the oxygen? So we got some oohs in the back, probably because it's a trick question. Why is it a trick question? It's not an ionic compound. Don't specify the charge on the oxygen. Okay? Oxygen is not a -2 charge. Okay? There is a video that will address some aspect about oxygen in that compound in 3 weeks. That's going to suck. You should watch that video when we get to it. Okay? So we have to be able to look at our compounds, quickly classify them, and follow the rules according to them. Make sense? When we look at formulas, I noticed this was a common issue. Let's ignore that middle thing. Not that useful to talk about. Okay, when we look at our formulas, what does that circled red 2 mean? There are 2 of whatever's directly in front of it. Directly in front of it is an oxygen, so that means there's 2 oxygens. So if I write the formula, PBr3, what does that mean? P is phosphorus.
Phosphorus, 3 beryllium.
Br is bromine. This would be an acceptable Lewis structure. However, drawing this would not be. drawing this would not be. Right? We'll chalk that up to panic. That's okay. It happens. Right? Make sure you read your formulas correctly.
Could you remind me again when there's two lines connected?
We'll talk about Lewis structure another time. Okay. So when we go through and look at formulas, what we're trying to do is just list out all the elements. So C6H6O6, saying there's 6 carbons, 6 hydrogens, 6 oxygens. We've grouped them all so we can put them out, right? Make sense? What does that mean is going on with this formula? HC2H3O2. Does that follow the same pattern? No. Why change the pattern? We want to mess with your head. No, it's not that. It shows us what?
Like what it links to?
So we might say it's what it links to. That's not a bad guess, except unfortunately for this compound, that's wrong. That hydrogen is not bound to that carbon.
I tried.
What kind of,
It has to do with the functionality of that compound. If you watch that really long, hour-long video, I apologize, right, that you watched it already. Right? You need to watch it, and what you'll find is that that compound typically is followed by an AQ, and it means it's an acid. So by putting that hydrogen out front, we're trying to draw attention to the reactivity of the compound. Right? We may alter stuff or alter our structure to draw attention to that reactivity. The same kind of thing is happening in the next one. Notice that that hydrogen is drawn out away from the structure, okay, or away from the rest of the hydrogens. Why? Now, why is it being placed out there? This is a connectivity. What I'm trying to show is that that hydrogen is connected to the oxygen right next to it. Okay? How do we know which one we're looking at? Experience is the only way you would know. Okay? So that's why when we look at most of our formulas, we'll stick to the same formula in the upper right-hand corner. We'll just list all the elements out, okay, with the numbers associated with them. We don't break them up, okay, to show anything about connectivity, because connectivity means you have to draw a Lewis structure. Okay? Just for giggles, you could go home, try and draw the Lewis structure for this. Yeah. I could add the other part of it, but I figured the giggles is just all I needed for this. Okay? Try and go through and draw the Lewis structure for that compound. You will probably have a hard time doing it because you don't have the rule set to understand how and why to put that together. Okay? It takes a little bit of practice. When do you learn the rule set to do that? In OChem, when it's important. Gen Chem, we don't care about structure, we care about the numbers of things, so we ignore structure. Right? So be aware that we won't evaluate the connectivity. We're largely concerned about reactivity, and that's really only in the case of the acids. Every other time, we're just listing them out. Make sense? Okay. So with that, because I didn't put the right slides in, we're going to jump straight to our PSS section, which is a massive rewind, right? Because we're going all the way back to the beginning of our textbook, talking about SigFig rules, their importance in how we manipulate our calculations, right? Which will gradually become more and more and more important, though kind of sidelined because you'll stop thinking about doing it. Right? So within the PSS, we have the types of measurements, significant digits, carrying SigFigs, also significant digits, and scientific notation. Those are our 4 major categories out of the PSS chapter. Okay? Most of this stuff will be kind of review because we've kind of talked about it in the lab. Okay? I know I haven't gone through it in a lot of detail in the lab. That's why we'll spend a little bit more time here. So, measurements. We did talk about this. Every measurement carries a number and a unit. Okay? You leave off the unit, you have nothing. You leave off the number, you can't do a calculation. Okay? So you have to include both the number and the unit in every single kind of calculation that you're going to run with a measurement. Right? We have different types of things that we can measure: distance, mass, volume, and time. There are all sorts of different units we could use. For distance, what do we use in the US?
Miles.
Miles. The rest of the world?
Kilometers.
Kilometers. Okay? Why did we do that?
Because we just don't know why.
Right?
We like to be difficult.
We wanted to be difficult. It originated largely back off of the inch, okay? Inch, foot, okay? All of those had historical contents. The inch was the length of the last digit of the king's thumb.
That's stupid.
Yeah, what? That's a good idea, because what happens when the king dies? You get a new measurement system. Okay? The foot was the length of the king's foot, and there just happened to be 12 of his knuckles lengthed out in his foot. Yeah, that's a lovely system to use. Right? That is the system that we then standardized somewhat and decided to continue to use through the US. Okay? The rest of the world adopted a different system, known as our metric system, okay, based off of a meter, and then varying the size of the meter by using certain prefixes to scale it by factors of 10. Okay? As opposed to, well, it's about half as long. Well, it's about half again as half. Well, it's about half again as half of half. Okay? So have you ever done construction? They're like, you need the 3/16. That's what they're doing. Okay? It's a stupid, awful system that will never change. Okay? Too ingrained into the populace, there's no way we're ever going to get that changed.
What?
Okay.
Should we go to the metric system?
To switch full metric or have metric switch full stupid. Right? It's just not going to happen. How about mass and weight?
Pounds or kilograms?
Pounds or grams. Okay? So we have, again, different units. Volume,
Ounces.
liters, ounces, cups, tablespoons. Sweet mother. Depending on what field you're in, you're going to get different measurements for volume and, for that matter, mass. Time,
Seconds, minutes, hours.
thank God we're at least consistent on one thing.
Fortnights.
Okay? Yeah, fortnights has died long, long ago.
Is that like
Okay.
2 weeks or something?
The biggest part is that we're looking at a metric system for nearly everything we do within science, so we need to understand how to convert them. Okay? Mass, we use a balance. I would recommend you download the slide and click that link because it is kind of a neat video. I just don't have the time to devote to it. Some guy gets really super excited about a round object. Right? But it is a neat round object, legitimately. Right? A piece of silicon. That's it. Volume measurements. Okay? Volume. It's a liquid. We can't measure the mass of liquids as easily because liquids change their shape depending on what container they're in. So they free flow. So we try to pour them on the balance, we end up destroying the balance. Right? So we can instead put them into a container, and that container we can have defined marks to allow us to decide what that volume is. Okay? So we got graduated cylinders, syringes, burettes, all that kind of fun stuff. Okay? Measurements and uncertainty. This starts to move us into SigFigs. Okay, again, a measurement is a number and a unit. What is the length of that metal rod? For those of you that might not be able to see, our projectors are so clear now, probably don't need the zoom in, but there's a zoom in for us. What is the length of that metal rod?
4.2 centimeters.
I heard 4.2. I heard 4.
You have to add centimeters.
4.0.
Yeah, I don't know about this.
Centimeters. I'm just going to add that as a big thing out there. 0.87? Oh, okay. 4.87. So what the? How are you measuring 0.87? Okay. Of those 4 numbers, how many of them are correct? Only 2. Why are those 2 correct?
Because SigFigs matter, so you can't just say 4 because
Our rule for measurements, all of the obvious digits must get reported. Okay? After that, you get 1 guess. It's an educated guess. Okay? If I guess again, I'm now guessing on a guess. That's not educated, that's dumb. don't do it. So 4.87, I appreciate you giving me that, by the way, okay, is unfortunately dumb because that 7 is a guess on a guess. The 8 was already a guess. Okay? Which means to say 7, you're now guessing on that value. We can't do that. So that is incorrect. Why is the 4 all by itself wrong? You didn't make the guess. Okay? You have to make that guess. I need some number out there. Make sense? Hi. If we want more significant digits, because we want more precision in our value, we need more markings. Okay? So this next ruler is more precise than ruler A, because I can report out to more decimal places.
I think it's more to the right though.
Make sense?
Because you know for sure it's 4.
I'm going to say that does make sense. Uncertainty, as we discussed in the lab, should always get reported with the measurement. It rarely does because it's really irritating to write plus minus whatever your uncertainty is for every single number. And we've got a confirmation from one of your classmates. Okay? So while it should be reported, we rarely do it. We just kind of worry about it if and when we need it. Which gets us to our significant digits. The numbers reported in your measurement are referred to as your significant digits. Okay? In a lab environment, because you're reporting things according to the measured value, you don't stress as much about significant digits because you took the measurement. You recorded those things. All of the data is there. In the lecture, you're not making the measurement. You are taking somebody else's measurement, which means they have to provide it to you with the proper rule sets to allow you to interpret what digits were actually measured and what digits weren't measured. Okay? So what makes a digit significant? Are 5 numbers? There's 5 numbers there, for those of you counting. The first one has how many sig figs?
2.
1. The second one has? 2. The third has? 3. The fourth has? 2. The last one? 1. Sweet! We need to review sig figs. Right? Sig figs requires practice to get used to manipulating them. What makes a digit significant?
Well, 1 through 9 is always.
1 through 9 is always significant. They hold meaning. Okay? And that meaning is a measurement. Okay? The trick on deciding the rest of those is deciding what the 0 means. Is the 0 a placeholder saying don't put your digit here? Or is it holding meaning, saying it is not a digit 1 through 9? The symbol that we use for those is identical. So we have to have a rule set to be able to explain when we're meaning what. That rule set is the 3, come on. Yep. The 3 rules that we addressed in class, okay, or in the lab. All digits 1 through 9 are always significant. Okay? 2, if there's no decimal point, then your 0 has to be controlled by significant digits to the left and to the right. Okay? At any place to the left, at any place to the right. Rule 3, if there is a decimal point, the 0 needs to be immediately preceded by a significant digit to count as significant. Okay? So let's try and rattle these off real quickly before we end class. How many sig figs in the first number?
3.
Next.
2.
Next.
3.
Next.
4.
Okay, so we'll start class talking about that one. Upper right.
2.
Next.
2.
Next.
3. No, 2.
2.
Next.
3.
Okay, so we have 3 numbers that we need to address to discuss sig figs. That's where we'll start class on Tuesday. Okay. We'll continue through the PSS chapter, which will involve dealing with calculations. But there we are.
What's the closest place I can